So in this recorded module, we're going to talk about triple integration in spherical coordinates. And this is the last new topic in vector calculus for 2276. There's one more thing we talk about in class, the Jacobian coordinate transformations. I'm not going to have a recorded module about that. You're not responsible for actually using that on the final exam or anything in the context of the course. We just talk about it so you've heard the term. This is the last new thing, and it's only partially new. We need this because we might be doing, for lots of reasons, but triple integration in the context of a divergence theorem might involve spherical coordinates. In previous years' exams, sometimes I'll have you set up a calculation, or an integral, I should say, in a triple integral in spherical coordinates, where you have to get the limits of integration correct and the integrand correct, and do that. So this is the last new important thing. It's another extension beyond cylindrical coordinates. Spherical coordinates there's a little more complexity now, number one. Number two, which is part of the complexity, is there are many different conventions for what to call the variables, and symbols actually get alternated between different conventions, so that's confusing. You just have to understand that is true, and in any given situation, whether the particular textbook you have in a course or whatever, they will have some convention they use for these coordinates, which we'll talk about, and as long as you stay consistent with that, it's fine. But there's no single right answer to this. People in individual fields will tell you that only theirs is the right answer, and they are wrong, because there are many. In preparing for the lecture, for this module, I just went to my shelf and pulled 3 different books off the shelf, and you get 3 different definitions of spherical coordinates. So generally within fields, like astronomy will do something, and in pure math they do something else, and actually in a lot of main physics and stuff will do something else, that sort of thing. So you get sort of norms within disciplines. So we are in 3-dimensional space. We have 3 coordinates. Here we're talking about a point in space that could be x, y, z, but we want to talk about it now in terms of rho, phi, and theta. Now rho and phi are new. Theta is the same as what we had before. So we have this point in space. The first description of where it is kind of simple. You just say, what's the total distance from the origin to the point? That's rho. Okay, so it's just a distance straight out to the point. Then you say, okay, well, that ray that forms by shooting from the origin right out to the point, defining rho, you say, well, what's its angle with respect to the z-axis? How much is it angled down? Okay, we call that phi. Okay, it's called the declination, polar angle. There's different words for it. Then finally, so you've got your ray out, you've got the angle down. Then you say, okay, well, now what's its angle with respect to the x-axis? And that's theta. Theta is the same as it was for polar and cylindrical coordinates, and that's actually why I use this convention. And it's the convention also that your textbook uses, the ZIL textbook. It's attractive when we're teaching because the theta stays the same. This is the same angle as we had defined before. It's actually quite common to call this phi and this theta, but we're not going to do that. Okay? And this is totally fine. Okay? When we have this group, one thing to realize is that what used to be r, or what was r in cylindrical and polar coordinates, which is the distance in the xy plane from the origin to the component of this point is in the xy plane. So if you take the point algebra P, shoot it straight down along z, and you hit the xy plane, this distance here is rho sine phi. That's just from this triangle here. Okay, so that side here is rho sine phi, opposite. This is just r. This is what used to be r. Okay? So we'll see that as we look through the rest of the math and spherical coordinates, we'll see this rho sine phi showing up. And if you look at it and go, oh, that's just the r we had before, some of these other forms make a little more sense. And it's a little bit easier to make that realization. When you have these 3 coordinates, rho, phi, and theta, well, rho can go from 0 to positive infinity, there's no limit. Phi goes from 0, which is along the z-axis, down to pi, just to pi, not 2 pi, just goes down to pi, which would be the minus z-axis. And theta, as before, starts at the x-axis and can go all the way around 2 pi. Okay. Now, Conversions are not surprising. And again, I identified the rho sine phi to make a connection to what we had before. If you know rho, phi, and theta, then you get x, y, z the following way. X used to be x was r cos theta. It's still that, but now r is rho sine phi. So x is rho sine phi cos theta, y is rho sine phi sine theta. This is the same as the conversion we had before, with the realization this is r. And then z is rho cos phi. Okay, this thing. This is phi, so it's this component here. Okay, and vice versa. If you have x, y, z's and want to go to spherical, rho squared is x squared plus y squared plus z squared. Rho equals a constant would define a sphere. Yeah. Tan theta is the same conversion we had before. It's the is y over x, so theta is the inverse tangent of y over x. And finally, cos phi is, well, it's z divided by x squared plus y squared plus z squared. So really it's z divided by rho, right? But if you have x, y, z only, then this is the conversion there. Okay, so phi would be the inverse cosine of this. Cool. Finally, we have the volume component, or the volume element when we do a triple integration. So the volume element for the triple integration now is a little bit more complicated, is rho squared sine phi d rho d phi d theta. Now, to make connection to what we had before for polar and cylindrical, if I just take this and say, well, it's rho and then a rho sine phi, this is just like r, right? So the reason we have these proportionalities in the volume element is because when we have these angles, for the same increment in angle, the further you are away from the origin, the bigger the volume element. So we have to capture that. Before, we only had one angle, and when we varied, so theta, you sort of had a, as theta got bigger, it got bigger proportional to r. So there was an r effect that corresponded to the theta term, and now there's a rho effect based on the phi term. So we have, this is kind of associated with the phi angle, this is kind of associated with the theta angle. Now we have the two of them. So there's two distances, and together they become rho squared sine phi. So it makes some sense. It's consistent with the arguments we had in cylindrical and polar coordinates. Okay? But this is the volume element. So when you're doing an integral, we have to define the integrand. What are we integrating? Get that in spherical coordinates. Then convert the volume element to spherical coordinates, just like this. Then we have to do the iterated integral and decide what order. We go in rho or theta or phi in what order, and then get the limits of integration correct. After that, it's execution the same as it has been before. So the example we're going to do for spherical coordinates is just an extension of the example we did in cylindrical coordinates, but now we're going to calculate a moment of inertia. For the cylindrical coordinate example, we did a center of mass calculation. So now let's do something a little, it's barely harder, just a little bit different, which is a moment of inertia calculation. Okay, so here's the problem. So calculate. The note module I'm using, by the way, is of course titled Triple Integration and Spherical Coordinates. You have that on the OWL site, and you can go through that. That covers all the things I'm talking about here with a little more language associated with it, and a little more slowly. Okay. Calculate the moment of inertia about the z-axis. Remember that moments of inertia are always with respect to rotation about some axis, right? So calculate moment of inertia about the z-axis of a homogeneous solid, which means the density is constant. So the density is not a function of position within the solid. Homogeneous solid bounded by the two spheres, x squared plus y squared plus z squared equals a squared, and x squared plus y squared plus z squared equals b squared, where a is less than or equal to b. So this is a thick-walled hollow sphere, right? We've got this is b, this is a, and this is a sphere, right? Okay. So thick-walled hollow sphere. and we want to calculate its moment of inertia for rotation about the z-axis. Okay, so the moment of inertia, just to remind ourselves, moment of inertia z would be, okay, it's going to be this triple integral of this, of the distance that a mass element would be away from the z-axis, which is x squared plus y squared, squared. So you want the distance away from the z-axis squared. That's what the moment of inertia is, because it's the second moment of the mass distribution. Okay, and then we have our density. Now, okay, yeah, here's one thing I need to talk about. Now, the problem, one of the tricky things with spherical coordinates, as we've written them, and I erased it now, when we say they are rho phi theta, rho. We like to use rho for density, we use rho for other things as well, and we use rho as a coordinate. That's why in some areas we don't like doing that. We'd rather use a different symbol. Now here we're gonna use rho. We just have to keep in our little minds that when we write rho in spherical coordinates, we're not writing density, okay? Right here, if I do, I'll give it a sub d. So this is a rho sub d. This is not the coordinate rho. This is the density function. In our problem here, it's a constant. I'm going to call it k, and we'll be done with it. Okay? But that's one complexity. Okay? But in general, this is the moment of inertia. So we have a density times a volume element. So this is a mass element. You have a mass element times its distance, radial distance away from the z-axis squared. Okay? And you sum those up. That's how we did moment of inertia calculations in first year. We just didn't do them for continuous distributions because we didn't have this kind of calculus in our hand yet. But now we have the power to integrate and solve for all the moment of inertia examples you would have in the tables that you could produce. Right? That's not terribly important. We have those tables, but this is where they all come from. So this is what we're actually supposed to calculate. Now, in our case, we're going to let the density, so we're going to say we're going to let K equal the density, which is a constant. It has units of kilograms, meter minus 3. Right? Okay, so that's constant. So what we have to do is get this integral into spherical coordinate form. Okay. Now, so the first thing we'll do, let's just go real slow here. So I sub z is equal to k times the triple integral over the region D, x squared plus y squared, where the region D is the region between these two spheres. Okay. And I'm going to, so dv, now I'll write that out as rho squared sine phi. And I'm going to write these in a not careful order. I'm not saying I'm going to integrate in this order yet, I'm just putting them all down there. Now, this is a mess, we can't have this. I've got a mix of different variable systems. So I need to convert this thing into spherical, and then we need to decide on the limits of integration. Okay. So converting those to spherical, there's a couple ways. You could actually do it by inspection, but let's just do it slowly. Let's just say, okay, x squared plus y squared. If we look at the conversions that we had, that was rho sine phi cos theta squared plus rho sine phi sine theta squared. Okay, so I've got a rho squared sine squared phi common and a cos squared theta plus sine squared theta. Cos squared theta plus sine squared theta is 1. So this whole thing just equals rho squared sine squared phi. Okay, good. That's in cylindrical coordinates. Let's now set the integral up. Okay, so I'm gonna say, okay, here's our moment of inertia. I'm gonna have k times something I'll integrate first, something I'll integrate second. Well, but first, second, third. Okay, I've got x squared plus y squared. So this is rho squared sine squared phi. Then I've got rho squared times rho squared sine phi from the volume element. And then I've got d rho, d phi, d theta. Now, if we just remind ourselves of our shape again, right? We've got a thick cylinder, two thick spheres centered on the origin. So rho clearly goes from A to B, right? We start at the inner cylinder, or at the inner sphere, and integrate out to the second sphere. So R will be between A and B. Okay. Sorry, R. Keep saying that. Rho will be between B and A. Now, then the rest of these things are spheres. So we're integrating over all of theta and all of phi. So phi and theta are easy. Phi will just go from 0 to pi, and theta will go from 0 to 2 pi. Now our distribution, our integrand depends on phi, so it's not that we can just pull that out. But it doesn't depend on theta. So what I'm going to do is we'll integrate rho first, then phi, then theta, even though I'm going to pull theta out right away. So rho goes from A to B. Phi goes from 0 to pi. Theta goes from 0 to 2 pi. Okay. Now I'm going to, since there's no theta dependence here, there's no theta dependence here, and there's no theta dependence here, this theta comes out, it just becomes 2 pi. So we have 2 pi times k, okay, 0 to pi, okay, and then A to B. And I've got rho to the 4th, sine cubed phi, d rho, d phi. Okay, so this is 2 pi k, 0 to pi. Okay, then I've got this special case, because this problem is so spherical. It's kind of like a rectangle in spherical coordinates. It's perfectly set up for spherical that the integrations separate, and we end up with a product of the integration over theta, the integration over phi, the integration over rho. And that separation can only occur because these limits on rho do not depend on phi, so phi can come out. So really I've got this integral, and then I've already done that integral, which was the theta integral. Okay. Now in the note module, I don't separate them out like this. I just keep them all together. So that way you can see there's two different ways. Okay. So let's get rid of the rho first here. So I'll just go, okay, 2 pi k 0 to pi. We'll deal with this little mess in a minute. Okay, so this becomes rho to the 5th over 5 b to a, right? So this thing becomes 2 pi k times, and we have, over 5 b to the 5th minus a to the 5th, right? There, times the integral 0 to pi cubed phi d phi. Okay, so we're almost done. There's a little trick. This is a trick we have to remember when we're doing these integrals of trig function sine or cosine to odd powers. So when we have this, what you do is, let's just take that integral for a second, okay? Just look at this. So we got pi 0. So what you do is you write it as sine squared phi, sine phi, d phi, okay? And that equals 1 minus cos squared phi, sine phi, d phi. Okay. You're like, why would you do that? Well, because then you get to make a substitution, right? You say u equals, so just let u equal 1 minus cos squared phi, so du d phi becomes minus, oh, sorry, not that. Sorry. Let u equal cos phi, right? So du equals minus sine phi d phi. That's where you get the connection there. So their integral becomes phi equals, right? And then we have 1 minus u squared minus du. right? And this is u, and so phi will be from 0 to pi. Okay, so this becomes yeah. Well, here, just do this really slow. Pi, phi equals 0. Then we have u squared minus 1, which becomes u cubed over 3 minus u. Phi equals 0 and pi. So that becomes, you know, we have cos cubed phi over 3 minus cos phi, pi and 0, right? This is pi. So this becomes 1 over 3, and cos of pi is minus 1, so minus 1 to the third. Minus 1, and then minus 1 over 3, and then we have plus 1. Okay, so this becomes, this is minus 1/3, so we have minus 2 over 3 plus 2, right? So that's equal to 4 over 3, right? 6 over 3 minus 2, so 4 over 3. Okay, so back here, our IZ integral, right, was 2 pi k over 5 b to the 5th minus a to the 5th times 4 over 3. Okay, so we can go, that's k times 8 pi over 15 b to the 5th minus a to the 5th. Okay, that's the moment of inertia of a thick-walled sphere, outer radius b, inner radius a, about any of the axes, actually, because they're all the same. Now, just back a step. So we have a thick-walled sphere. Do we expect it to have a non-zero moment of inertia around the z-axis? So remember, back to physics, what does that mean? To have a non-zero moment of inertia means if you were rotating this thing, does it have energy associated with the rotation? Does it take work to rotate this thick-walled cylinder around one of its axis? Just imagine if it was a big, thick ball and you had to rotate. Yeah, for sure it does. There is energy associated with that because of this mass distribution. That's what the moment of inertia quantifies or represents. So yeah, of course it should have a moment of inertia. So now let's ask a question here. Does this make sense? So the first thing is, okay, do the units make sense? What do we expect the units of moment of inertia to be? They should be kilogram meter squared, right? And so if we look at this, okay, so we know that K had units of density, okay? So the units of I, okay, so we have units of K, which are kilogram meter to the minus 3. And then I've got b to the 5th. A and B are meters. So this whole thing is meters to the 5th. So this is kilogram meter squared. So yeah, it does have the right units. And this is what's so important and powerful. But two things. If the problem had said the inner radius of the sphere was 1 and the outer was 2, we would lose the units because 1 and 2 would filter into the math and you wouldn't see where the units were unless you were really careful about keeping them out separate. It's why it's actually nice to call things like A and B, because then when you're done, you know, oh yeah, A has got units of meters and I've got A to the 5th. If this was just 1 to the 5th, it just looks like 1, and you don't feel like you have the units with you anymore. The other thing is why it's important to give density some units. Don't just say density is uniform, just say, yeah, it's a value K, and K has units of kilogram per meter cubed. That way when you're done, you can do a unit analysis and make sure this makes sense. So yeah, it makes sense that we have these b to the 5th power. Look kind of weird when we were in there. At this point, you might go, geez, b to the 5th, that seems weird, but yeah, it's true. The other thing you can say is, well, are the limits good? So, I don't know, if A is constant and B goes to infinity, the moment of inertia goes to infinity. Yeah, it would. If B equals A, okay, so in other words, if you can make A go up to B, so when they equal each other, the thing becomes infinitely thin, it has no mass, and the moment of inertia should go to 0. So as B goes to A, the moment of inertia goes to 0. Yep, that's good. If A is 0, then you should have the moment of inertia of a complete sphere, which is truly B to the 5th, but you'd have to know that separately. Okay? So this all does feel good and make sense, okay, in terms of units and stuff. Okay? So that's our, this worked example of the spherical coordinates. We obviously chose a problem, and you do this, right? There are some that just become very easy to do when you're in the right coordinate system. Doing this in Cartesian coordinates would be quite difficult because you're integrating lots of square roots and stuff, and it would be gross, right? But spherical is natural, and that's the whole point of these different coordinate systems. If your problem is spherical, then you want to use spherical coordinates. If your problem is cylindrical, you want to use cylindrical coordinates. There's definitely cases where the choice between cylindrical and spherical is a bit of a judgment call. Okay? Usually it's like, definitely we're going to do Cartesian, or we're going to do cylindrical / spherical, one of the two, that sort of thing, right? So there's a bit of hybrid in there. But that's a great example. This is a totally valid question we could ask on an exam or anything, not too difficult to do. You can do analysis at the end and make sense of it. So that's the last new thing in the course. The rest of the vector calculus portion of this course. So the rest of the work we might do is showing up more recorded modules of example problems. But that brings us essentially to the end of chapter 9, which was a big chapter in ZIL, all of vector calculus.